Hi, this is Paul Schreiber from Synthesis Technology. I'd like to welcome you to my first of many tutorials about the CAD tools I use to design my synthesizer modules here at SynthTech. The first tool I'm going to talk about is called Tina. Tina is a SPICE simulation program which uses a graphical schematic interface. It's very easy and powerful to use. I encourage everyone to go to www.tina.com and download the demo versions and check the software out. Let's get started. What we're going to design today is a simple RC filter and show you how the sweeping tools in Tina can be used to generate the frequency response. We're going to use what's called the basic library, which just simply has resistors, capacitors, inductors and transformers, voltmeters and batteries, that kind of thing in it. Very simple. But Tina comes with thousands and thousands of different models of everything from op amps to RF transistors to even microcontrollers, where you can actually run code in real time on the screen and look at digital signals as well. But we have to start somewhere, so let's start with the simplest little synthesizer circuit I know of, which is an RC low-pass filter. So we're going to use only 4 elements for that. We're going to use a signal generator, which is a symbol here. We're going to use a resistor, a capacitor, and a voltmeter to look at our output. Now notice that these parts have values already assigned. Now it uses the last value that you picked, and I happen to use these for my tutorial, so I kind of cheated by preloading those values. But notice that the values are also in lowercase. One thing to remember is that SPICE, as well as any SPICE program like Tina, is case sensitive. So be sure that you always enter your values in lowercase. The editor is very straightforward. You can right-click and rotate, drop and drag functions. I'll just kind of make it a little pretty here. Our connection tool, we have to wire it up. It's with this little pencil. It's fairly clever. So you just drop and drag. Oops. Move that over. Drop and drag. That's not very pretty. There. Now, we could simply do this. We could come over here and connect this to here, connect this to here, and say, all right, this is my circuit. I'm all done. I have a voltage generator, RC, and a voltmeter. Let's do a simulation. However, this exact circuitry would not work. The reason is that you have to have at least one ground node. Differential components, and there's not reference to any ground. They're just referenced to each other. So you have to have a ground. So let's give our SPICE circuitry a ground. Use the wiring tool. Now SPICE will be happy. It has its ground. This is also always called node 0. So we have node 0, node 1, and node 2. Now we're ready to run it. But before we run it, what I'd like to do is add another voltmeter across the resistor. So I'm going to simply drag this over here. I'm going to connect a voltmeter so I can look to see the value across the resistor. This way, I'll be able to know that I can measure voltages that don't have to be referenced to a ground. Now that we have our circuitry designed, we need to tell Tina that we wanted to see a sweep of voltages from our voltage generator. So we do that in 2 steps. The first step is we're going to right-click on Properties and tell it we want to see a sine wave. Notice that the default here says unit step. We don't want a unit step. A unit step goes from ground to some voltage, which happens to be 0, which means it does nothing. So we need to click on those little tiny 3 dots, and sure enough, we have a large selection of different voltage sources. So here's our sine wave. Now, one thing to note about SPICE, and this is a quirk of not just Tina but all of SPICE, is that it does the amplitude in half cycles. So that it says amplitude of 1. That's not 1 volt peak to peak. That's 2 volts peak to peak, where the half amplitude is 1. So that's annoying, but that's the way SPICE goes. There's also things for phase and frequency, but we're going to put those into the sweep menu, which we'll see in just a second. Click OK. So now we have a sine wave sweep. How do we actually tell it to sweep? That's called an analysis. So we're going to go to Analysis, come down to AC Analysis, slide over to AC Transfer Characteristic, and this opens up our sweep menu. Now you would say to yourself, how did you know that? The answer is, because I used the program for 20 years, that's how I knew it. The start frequency and the end frequency you can type in. The number of points is really not important. I always use 200. I don't think there's an advantage of using more than that. You want to always do a logarithmic sweep, so you're linear in dB on the amplitude, and we'll show that in the next screen why that's important and easy to use for filters. We're going to do amplitude and phase for this example, although most people don't really care about the phase, they just care about the amplitude. We're going to do amplitude and phase. We're going to click OK and see what our wonderful little i3 computer can do. La-di-da, and we're done. Look at that. Notice it generates a nice pretty graph. This happens to be the 7th graph because I haven't cleared my graph cache. And you see these two traces. There's a red one and a green one. Red and green, red and green. But you don't know which one's VM1 and VM2. This is a little quirk that I do not like about Tina. So it doesn't auto-append any kind of label. They make you do a mouse hover. So look at my mouse. I'm going to hover up over the green. When it turns to a crosshair, down the bottom it says VM1, the capacitor. If I hover over the red, it says it's VM2. So you have to do this little mouse hovering. Of course, what you could do is simply instantly add a text box and go, green is VM1, and go, OK. I'm going to put it right there. There we go. Green is VM1. Except I mistyped it. Oh well. Green is VM exclamation. So now we can look at our graphs, and sure enough, the green graph does look like a low-pass filter. What's interesting is the red graph, to me, sure does look like a high-pass filter, doesn't it? In fact, that is true. But notice what's important. It's a low-pass filter with respect to ground, which is the same terminal that the generator is. But the red is not with respect to ground. It's across the resistor. So this is a differential measurement. If you took a scope probe and hit ground and looked at here or here, you wouldn't see that. If you looked over here, you'd see the function generator. If you looked over here, you'd see the capacitor. You'd have to have a differential probe across there, and then there's your high-pass filter. The other thing that's interesting is, look, they cross at this little point right here. Well, if they cross at the same amplitude, that means the voltage here is the same as the voltage there. And folks, that's our cutoff point. So let's look at the A cursor. We're going to click on A, click on the green. It anchors the A. We're going to slide A over. Let me move this over here. It's our little readout. And sure enough, by eyeballing it, where it's minus 3 dB, it's at 1.6 kilohertz. So here's our frequency, and here's our gain. And this is what I really like about this program. This is, to me, worth all the money in the world. You can just simply type in the value here of minus 3 dB. It will automatically put the cursor and it will back calculate for you. This is invaluable. I use this feature hundreds and hundreds of times. This is why I love Tina over all the other SPICE programs. It lets you type in the cursor and actually go backwards. You don't have to eyeball it. And sure enough, it's 1.59, so if I do 1 over 2 pi RC of that, I'll get 1.592 or something hertz. So that's our cutoff frequency. You can also, interesting to see on these graphs, let me move this down, is that the area in here is equal to the area over there. They're mirror images. So that means that energy is conserved. So whatever energy our functioner pumps out, it's going to dissipate the same energy here. It's not equal energy, but the area under the curve is equal on both sides. Now let's look at the phase. So we're going to use our little B cursor. We're going to go to B, click on green, because that's our output. It brings up this nice new graph. I want to anchor B and slide it over to where A is. So I want to go backwards. I'm going to type in the frequency of 1.59 over here. Okay. And now you'll look and see the phase shift, which is down here on green, is minus 45 degrees. It's not exact. It's rounding off because this is not exactly the cutoff frequency. So at the cutoff frequency of 3 dB down, it's a 45 degrees phase shift relative to what? 45 degrees from what? From our function generator. It's negative. What does that mean? That would mean if you looked at it on a scope that this is behind. So if this voltage was at its peak of 1 volt, this voltage would be behind a little bit. So that's called lagging. If you look at the resistor, it's at plus 45 degrees down here. So it's leading. The voltage here is leading. Now this is also something that's very confusing when you're sitting in double E class going, wait a minute, how can you lead the voltage if the generator just turned on? Are you telling me that if this thing turns on, it's a millionth of a volt above ground, that this thing is going to be leading, which means the voltage has to be higher than that? How is that possible? Well, the answer is it's not possible. You can't do it. You have to run through several cycles in reality, and then it does it. This is what's confusing about electrical engineering and causes many students to become website administrators. So this kind of concludes what I have to say about Tina. You can see it has a very powerful graphing option here. It's a very easy schematic thing. And just to show you how you can simply change a value, if I go to this capacitor and go down to properties, and I make it 10 times bigger, if I go 100 nanofarads and say OK, then I get rid of this graph. I'm going to run it again. Analysis, AC, transfer, remembers the values. OK. Notice it added Bodhi 8. Now we've shifted. Now we're roughly here. Again, we're going to pull this over, type in -3. Well, I'll be, it's exactly a 10th. So I changed the capacitor 10 times in value, and it went from 1.59 to 159. So it's proportional. So that's what we call a linear circuit, that if I change this by a percent, then, which happens to be some percent, then it's going to change another percent. This one happens to be exactly 10 times, goes down by 10 times. That's not always true, but in this case it is. So now you can see that by changing this by a factor of 10, my cutoff frequency dropped by a factor of 10. The phase is the same, the area under the curve is the same, it just shifted the cutoff frequency down. Well, that concludes this tutorial. Thanks again and hope to see you next time.